So let's begin our review of this past free response question on spectrophotometry. It's an older question, but a very applicable one that goes over many of the concepts that we're studying here in terms of identifying the molarity or concentration of a colored solution. So let's be crazy and start in order with number 5. Now, of course, number 5 is the 5th question of this free response test, but it's the first one that we're going over here in this video. So a student is instructed to determine the concentration. Of course, the concentration we're talking about here is molarity of a cobalt chloride solution based on the absorption of light. Okay, now looking carefully here, we've got cobalt. Cobalt is a transitional metal, and that transitional metal is in the middle of the periodic table, and it has something called d orbitals. And as we've been talking about in class, these d orbitals, okay, come in contact with electrons from a ligand. A ligand, okay, is going to be a chemical that has an electron-rich area that is attracted coulomically to the very positive and probably very small cobalt ion. As we've been learning, if an ion is multiple charged, greater than 1 or 2, and it is smaller, okay, as in the case of many transitional metals, that ligand's electrons can be pulled not just close to that positive ion, but into the d orbitals. And sometimes, because of the shape of the d orbitals, some of those electrons will go right into those orbitals and destabilize them, and then some don't. And that's what splits and makes that gap, so that light can be absorbed, or part of the what? Part of the visible spectrum can be absorbed. That's the key here. If something has a color, we can use spectrophotometry. And it has a color because it absorbs a portion of the wavelength because of a small gap it has with its d orbitals. These boxes represent the not very good boxes there, but these are the orbital notation for the d orbital, or the d orbitals, or the d sublevel, I should say. And as we've seen in class, these guys are supposed to be degenerate in the same energy level, but they have a little bit of a gap here, as some of the electrons, based on the shape of the d orbitals that we looked at, have gone into those orbitals. Bottom line is, okay, it has a color, it absorbs part of the light. Spectrophotometry measures, okay, how much this chemical, or this, in this case, cobalt, can absorb. And it makes sense. If you've got more of it, it absorbs more. Any case, here's the concept, or here is how most of these labs are set up. So they're going to give you a standard amount of a solution of cobalt chloride. Now that sounds weird, because this lab are after its concentration. So why would they give me a concentration? Well, all spectrophotometers, all they can really measure is how much, okay, light is being absorbed. In truth, they measure the transmittance, how much light actually leaves the cuvette based upon how much is being absorbed. But a negative log of the transmittance is the absorbance. And the absorbance, of course, is how much of a certain wavelength of light the chemical is absorbing. So why are we given a known amount? Well, the equipment, the spectrophotometer, doesn't know anything about concentration. All it knows is there's a proportionate relationship. If the absorbance is higher, hey, that means you're absorbing more of the light, which means you have a higher concentration, or a higher molarity. So we need to essentially calibrate our spectrophotometer so it kind of knows the molarity associated with a known amount of absorbance of light. Okay, kind of like what we've done in past labs. All right, so what they have is a 0.1 molar solution that's given to you. Okay, and from this 0.1 molar known solution, okay, we prepare standard solutions. These are standards because we're going to use them to calibrate our spectrophotometer. And so what we do is we do a dilution. Okay, we do dilution, and sometimes they call this a serial dilution. We do a bunch of dilutions. Okay, and a serial dilution just means what we're going to do is take this solution, and then we're going to dilute it to 0.02 in this case, and then 0.04, and then 0.06, and then 0.08. If it's a serial dilution, as we're going to do in our lab, we'll take from 0.02, we'll make from 0.10, we'll make 0.02. And then from the 0.02, we'll make the 0.04. From the 0.04, we'll make the 0.06, and that's why they call it a serial dilution, one from the other. But we're going to make these standard solutions from the known amount that we start with here to essentially make something called a Beer's law graph that, again, will help us calibrate and figure out what the absorbance is for a known molarity. Here's what we do know about absorbance. Absorbance, and this is from your reference table, is equal to big A, which is the amount of light. Okay, it's a negative log of the transmittance, but it just means how much light is being absorbed, is equal to some constant, okay, an absorptivity constant, okay, times the path length, that's the path of light through the cuvette, which is about 1 centimeter, and times the concentration, and that, of course, is the molarity that we're after. So if you notice, higher the absorbance means what? There's more chemical that's absorbing the light. You're going to get more higher concentration. Okay, and of course, a constant here, and this is 1. That's the distance between the cuvette. Okay, and of course, that cuvette that I'm talking about is a little rectangle by which we put a plastic container by which we put the fluid, okay, to test, okay, and the light goes through it, okay, and the distance here is about 1 centimeter, and that's why we always kind of pick B as 1 here, but it may not be in different problems. Okay, so we got some background here. So let's get to the first question. Describe the procedure for diluting a 0.1 molar solution to a concentration of 0.02 using distilled water and a 100 milliliter volumetric flask and a pipette, notice, or burette. So they want you to use one or the other. Include specific amounts where appropriate. So we're going to take a more concentrated solution, which is 0.10 molar, and we're going to dilute it, okay, to 0.02 molar. And they want you to describe that procedure. Well, my friends, we did this, okay, in our previous lab. That's why we spent so much time doing this and writing it up. So you should recognize right away, if we're going to dilute a known solution, we should really jump to the dilution formula, okay? And that's very simple, is MV times MV equals MV. Okay, so I'm going to take my 0.1 molar solution, and we're going to figure out how much of it, okay, that's my X, or unknown, that I need from this more concentration solution to make my new solution molarity is 0.02. And since I'm going to use a 100 milliliter flask, that means I'm going to make 100 milliliters of it. Okay? And I'm going to make that in liters. Okay? And there is my setup. So I'm going to solve for how much of this more concentrated solution that I need. Okay? And from that, and this is really important, from this volume, I'm going to dilute it to 100. Okay, that's why they call it the dilution problem. And we did this in our last lab, so it's important you recognize that. So let's go solve for X. So what we get is, we get, okay, 0.10x, okay, equal to the product of 0.02 times 0.1, and that's going to be 0.002. And of course we solve for our X, and I know some people don't need to write this out, but some people do. So we're dividing by 0.10, and of course X, all right, we're dividing by, this is going to get bigger, so this is equal to 0.02. And what we set, and because this is a volume, and I set this up to be liters, that would be liters, okay? Now, if you want to follow the units here, this is a molarity, okay? So this is molarity, so this is mole over liter. And what I multiplied across here, okay, was the product of these two numbers. Well, this is molarity times liter, that gives you mole. And what you can see here is moles cancel, and 1 over liter gives you liter. Okay, so if you want to follow that. So what does this mean? So what this means is I need 0.02 liters of it. Okay, and what that means, of course, is I need 20 milliliters. So I need 20.0 milliliters of this more concentrated solution. And what I'm going to do with that, of course, is I am going to pour that into a volumetric flask. So let's write that out, because you have to describe. So I'm going to get rid of this. This was just to explain some things. Okay, so what I would write here for my answer, okay, is that I would take, I would measure. Now, measure with what? You can use a pipette or burette. So it would basically burette or measure 20 milliliters and 20.0. I'm going to carry 3 sig figs here. All right, but I probably am allowed to have 2, but I'll just carry 20.0 milliliters. Probably look at my numbers here. Yeah, 2 significant figures. Let's stay consistent here. And how I know that is because if I look at my numbers that was given to me, okay, I can see that I was given 2 significant figures here, 2 significant figures here, and I'm looking to make that. So from my 2 significant figures or my least significant number, it's going to be 20 milliliters. So measure 20 milliliters. Let's stay black. 20 milliliters from a burette or pipette. I'll say measure from a burette into a 100 milliliter, okay, volumetric flask. And then dilute with distilled water to the 100 milliliter mark. Okay, so that's it. All right, and you probably want to mix, okay, probably put a top on it and mix and shake up the flask so that it makes a nice homogeneous mixture. Okay, so probably stopper and mix the flask as well. Okay, so that's it. So that's how you use the dilution formula. Let's go on to the next question. Before we start the experiment, again, the idea of this experiment is to find an unknown concentration of cobalt chloride, which has a colored solution. We're going to take this known 0.1 molar solution, put it into a cuvette. Okay, that's a little cute little rectangle plastic that will fit into our spectrophotometer. Add the solution, and then we're going to measure its absorbance or its transmittance. Don't forget that transmittance is just the missing light. Okay, so if I was to draw a much better cuvette here, let me just do that. Again, I want to make sure you understand the concepts. So here is my cuvette. Okay, it's my best rectangle. I'm going to fill it with some cobalt chloride solution, and we'll give it that color. I think it's more of a purpley color. Any case, what we're going to do is we're going to shoot some light at it, and this is going to be the light that gets through. It's going to be less because the reason why this compound has a color, it absorbs part of the wavelength, so some of that light won't get through. And what gets through is called transmittance. So transmittance is what we call the light that gets through. And because people don't like dealing with inverse relationships, okay, what does that mean? Well, as I increase the concentration of cobalt chloride, there's going to be more of it to absorb more light. So as the concentration goes up, the amount of light that gets through goes down. No one likes that, okay? So what we do with the transmittance is we do the negative log of the transmittance. and that gives me absorbance. So notice, hey, okay, so when we run the experiment, it makes sense that negative log kind of turns this around, makes it a more positive value, right? Because as the number gets smaller by making it a negative log, it becomes a more positive value, as we've done with acid and base pH. Okay, so any case, that being said, what we're doing is when we put the sample into the spectrophotometer, we're looking for the greatest ability. It's going to absorb a wide range of different wavelengths. Remember, wavelengths are the individual energies of the different photons of light. Okay, what we're looking to do here is tune our spectrophotometer for the wavelength of light that it best absorbs. So the first thing we do is we put our standard solution into the spectrophotometer and we see what we call peak absorbance. If we use absorbance, we look for the peak absorbance right here. This is the wavelength of light, or the photon of light of a certain color that it best absorbs. And we try to find that value, and we set the spectrophotometer just to read that value so that we have a lab that is reading the changes of just that wavelength that it is best suited to absorb. It will give us the greatest data. If we set our spectrophotometer to places where it doesn't absorb that well, we're going to have some error or some reliability issues. So we want to set the spectrophotometer to the type of light that it best absorbs, okay, so that we have a more accurate lab or a procedure, especially when the concentrations start getting low. So in any case, we're going to read that value, and they're going to give you an acceptable range. Now, whether you use absorbance, which I like to use because I like to think in terms of, hey, the better that it absorbs, the higher it is. For transmittance, because we're talking about the missing light, it's going to be going downward. So if you're doing transmittance, okay, where we're dealing with that inverse relationship, okay, or where that missing light is, we're looking down here. But absorbance is what we'll see most of the time. So in any case, we're looking for, okay, this 480, or I guess, I don't know, 490-ish. All right, so make a good estimate here. I think it's around, I don't know, this is 510. We go by tens here. 480, 490. Okay, 500, 510, 520. So it looks to me like more like 510, and that's nanometers, and that's of course the size of the wavelength of light, which corresponds to a unique type of light that it absorbs. Okay, they're going to give you a range in the answer booklet to be 490 to 520. So I think that's pretty darn generous considering the peak is below 520. Any case, so 510 nanometers. You're just looking for the peak, and again, all we're doing is tuning the what? Spectrophotometer before we do the experiment to best look for the type of light it best absorbs, so we can get the most accurate results here. All right, so moving on. Okay, so now we begin the lab. And so what we do now, after we have tuned the spectrophotometer to read the best light that it absorbs the best, and we have made our solutions, okay, our standard solutions, what we're going to do is take the cuvette, okay, with these solutions, and we're going to put it in the spectrophotometer, and it's going to read the absorbance of these standard solutions. Remember, the whole purpose of these standard solutions that we made from a serial dilution for a more concentrated value is so that we can kind of calibrate the spectrophotometer. Remember, the spectrophotometer doesn't know anything about absorbance with an exact amount of light being what? Absorbed. I mean, it doesn't know the concentration for the exact amount of light being absorbed. Absorbance is equal to A, B, and C. Well, A is a constant, B is the path length, which is about 1 centimeter. Okay, so we need these values to exactly calculate both of these, but we're going to use the relationship of absorbance is proportionate to concentration. Hey, if there's more cobalt ions in the solution who are absorbing a certain wavelength because of crystal field theory, then they're going to absorb more. That's all I really have here. So we're going to do this. We're going to take these solutions, pour them into the cuvette. Okay, so the 0.02. And then we're going to read the absorbance that the computer or the spectrophotometer reads. And it's going to, and we're going to make a plot. We call this a Beer's law graph. And Beer's law states that there's a linear relationship between the changes in concentration and the change in the absorbance. So we're going to put the 0.02, and we're going to read the absorbance, and we're going to put in the computer, just like we did for the acid-base titrations, we're going to tell the computer that the concentration is 0.02, and it's going to plot that. Then we're going to put the 0.04 in a new cuvette, okay, and then we hit enter, and when we tell it it's 0.04, it's going to make a new plot. Then we're going to put this concentration in a new cuvette. We hit enter, it reads this, we put in the actual concentration, and we keep doing it till we have gone from the lowest concentration to the highest. And then we make a best fit line called a linear regression. So a linear regression we will make, and that's just a best fit line, and our computer will do that for us. All right, and we will get actually, okay, y equal mx plus b data. We will get that. All right, and we will solve for the actual concentration of the unknown sample. Remember, we're using what? We're using these standard solutions to make us a what? An equation to solve for the unknown. So what we'll do in lab is we'll solve for the x. The x, of course, is the concentration given a certain what? Absorbance. So what we'll do in lab is we'll put the unknown concentration into a spectrophotometer. Okay, it'll give us an absorbance. So we'll have that value for y. It'll be the absorbance, right? That's your A there. And because we did a linear regression, we will have the slope already. We will have the y-intercept. And all we'll have to do is solve for x. The absorbance will be read on the computer. The slope of this Beer's law line will be given to us. And so will the what? So will the y-intercept. So when we solve for x will do this. We will get what? A. All right. And we'll divide that by b. I'm sorry, divide that by m. And that's minus b. And so we will solve, okay, for the x. The x-axis is the concentration by using the known slope that's given to us when we do a linear regression, by using the known y-intercept that we'll get from the linear regression, and the absorbance that the computer gives us when we put the unknown sample, and we'll solve for that. So we're basically, if you see what we're doing, we're using the standard solutions to come up with the exact linear relationship, and then use that linear relationship to solve for the unknown. That's how we're going to do the lab. Now here, because they have the graph given to us, okay, all you need to do is do this. So the absorbance of an unknown solution. So they gave you the unknown solution, okay, and they're telling you that the absorbance is 0.275. So they put the unknown sample into a cuvette. The spectrophotometer gave you a reading of 0.275. Well, using this linear line, okay, they want to know the concentration of the solution. Well, all you need to do is, once you have this calibrated line, is take this 0.275. This is 0.25, right? So 0.275 would be right in between, right? 0.275 is right there. Okay, now, of course, my drawing a line is not easy here, but so what I'm going to do is go across, and I'm about right here. I'll draw that in a different color. What color that is, I have no idea. Okay, this is 0.040, so this is 0.050 for this line here. We're a little bit past it, so we're going to have to make some estimations here. This is 0.050, this is 0.055, so 0.0525, so 0.0525, and they're going to give you a range. That's what I get for my molarity, okay, for this. And they gave you an acceptor range of 0.0045, I'm not sure how you get that low, to my number 0.055. Okay, it's not my number, but it's a little higher. So they gave you a nice, easy range. What we were doing is trying to find this value here. So we're just using the graph, okay? And again, a straight edge would help a little better than what I have here, but that's all they're asking is to just read the graph. Now, obviously a very simple one-point question, but we spent time here to understand what we're going to do in class, okay? I would rather use the y equals mx plus b to get this exact position than what? Estimate using the graph, but they do this a lot. So that's the answer for C, and how we do that, moving on. So D says, Beer's law is an expression that includes three factors that determine the amount of light that passes through a solution. Identify two of these factors. Well, from your reference table, absorbance, negative log of the transmittance, equals A, B, and C. So they want you to identify two of these factors. The amount of light that passes through a solution is tied to absorbance, okay, because if a compound absorbs light, there's less light going through. Okay, if it absorbs less, more goes through. So they want you two out of these three factors. So A is the absorptivity constant, and B is the path length, that is the length or distance light has to travel through. And all of this is on your reference table. And of course, this is your molar concentration, or concentration. So they just wanted two out of the three, and then give you a point for just two of them. All right, that's pretty darn simple. Let's go on to E. The student handles a sample container, test tube or cuvette that holds the unknown solution and leaves fingerprints in the path of the light beam. So here's my ugly cuvette. I know you can't wait for me to draw another one. So here's my cuvette. Okay, I think I'm getting better. Oh, I think I am. Okay, so that's going to fit into, if you look overhead of a spectrophotometer, there's a little place where you insert it. And there's going to be a place like right here where they shoot the light, and there'll be a detector here to measure how much light goes through. Yes, good stuff. But any case, okay, a student handles the sample path, right? Okay, handles the sample container, the cuvette. That's what this is, the cuvette, that holds the unknown solution and leaves fingerprints. So if I leave fingerprints on, or oils from my hands, and I put this into the spectrophotometer where the light passes through this side, okay, how do you think this will affect the calculated concentration of the unknown? Explain your answer. Well, if you're going to put more things in the way of the light, okay, you can best bet that's going to affect how much light goes through. So the presence of the fingerprints will add an additional factor that will absorb more light. And if something is absorbing more light, there'll be less light, okay, reaching the other side of the detector, which is on the other side here. And so what we'll have is we'll have a higher or a greater amount of absorbance than there really should be, okay? Therefore, if you have a higher amount of absorbance than you should have, then remember it's equal to ABC, you're going to have a greater amount of concentration. Higher the absorbance, the more light being absorbed is reflected in, hey, having more of the solution there to accept those wavelengths. So by having something in the way of the light that's going to scatter or absorb the light, what it's going to do, of course, is going to increase the amount of light, okay, that is absorbed, or decrease the amount of transmitted light that gets through. It's the same thing, okay? And so that's the answer. So to explain this, okay, so you need to say that there's an increase in the concentration. There'll be a greater than expected concentration, or an overestimation of this concentration that we're accepting. And that's due to the fact that we have what? We have more absorbance going on due to a extra chemical or chemicals that are on the outer edge that are in fact doing the absorption. Okay, so that's the way you would write that. It's a 2-point question. You get a point for saying there's an increase in concentration, and you would have to explain that because of the fingerprints leaving oils or leaving extra chemicals to absorb or scatter light would actually increase the absorbance, okay, or decrease the light that gets through. All right, so that's how you would write that. That's a 2-point question. All right, I don't think I need to write that out. All right, so F. All right, and the last one. Why is this method of determining the concentration of cobalt chloride solution appropriate? Okay, whereas using the same method for measuring the concentration of NaCl would not be appropriate. Okay, this is a great question. Okay, as we've talked about before, okay, cobalt chloride is a transitional metal, which means its radius is smaller than more reactive metals, and then when it loses electrons, okay, it becomes even smaller. The cobalt here is +2. So it lost 2 electrons, and losing 2 electrons will make the resulting ions much, much smaller than the cobalt. All right, so we've got a small ion that's +2. High coulombic attractions is going to pull a ligand in this case, it's going to be the chloride ion. It's going to pull the chloride ion's electrons right into the d orbitals and get in the way or interfere with those d orbitals and destabilize some of them, not all of them, create a gap. The bottom line is cobalt chloride creates a color. This is a colored solution. You don't really have to mention crystal field theory. Okay, it's not part of the AP, but boy, I like to explain why. And it's colored because it's a transitional metal. And boy, I feel like that is missing the boat in terms of why. Transitional, I can do this. Transitional, okay, I guess I could just transitional, I could do that. Transitional metals, okay, have colored solutions because of crystal field theory, or crystal field splitting, however you want to call it. And that's just due to being what? A high positive pulling in electrons into its d orbitals, and understanding that it doesn't pull them all into the d orbitals. Some are what? Some go in between, and some go directly in, and it creates that gap to absorb. Small gap, because visible light is what? Very low energy, okay? And sodium is a group 1 metal. It's a big atom. And not only that, it doesn't have any d orbitals. So it's a colorless solution. And being colorless means that it doesn't absorb any visible light. Meaning what? It is worthless in terms of spectrophotometry. So in any case, you get a point from this question. And so a cobalt chloride solution absorbs visible light. It has a color. A sodium chloride is colorless and does not absorb visible light, and that's all they're looking for, but I love to teach you why it's colored and why sodium's not. So sodium is colorless, it's non-transitional, it doesn't have d orbitals, it's not, when it becomes sodium plus, okay, it gets smaller, sure, but it's still too big and coulombically not to drag in a ligand in. And of course, it doesn't have the d orbitals to do that anyway. All right, so that's that. And so by going through this, hopefully you get the idea and get a better feeling of what this lab's going to be about. Because we're going to do a lab where we do percent by mass of copper. And we're going to not deal with cobalt, we're going to deal with the copper, that blue-green color. And we're going to try to figure out the percent by mass. Percent by mass of what? Copper in brass. Okay, and how do we do that? Well, we do that by figuring out how much mass of copper we have in the sample. And how do we do that? We need to know its concentration, its molarity. How do we do that? Spectrophotometry. If we have its molarity, hello, okay, and we know how much volume we have of the solution, we can solve for moles. And the moles give us our mass. And if we have our mass of copper and we have the mass of our total solution, this becomes a gravimetric titration, right? If we know the mass of the total solution, okay, or I say mass of the total piece of brass, all we need to do is mass of copper that we get from the grams, that we get from the moles, that we get from the concentration, hey, over the total mass times 100, we'll get our what? Percent by mass of copper. Okay? Any case, hope that helped.